Good? Oh, you can hear me? OK, great. So I have a little bit of light entertainment, hopefully, before we go to lunch. So I want to talk about this functional Perl, which is about the Knuth-Morris-Pratt algorithm for substring search. So let me quickly describe what that problem is. So I have this sentence here, which is, as my mama said to me. And suppose I'm looking for some other string in this piece of text. Say I'm looking for the string mama in this sentence. So I'm going to call the big string the text, and the thing that we're looking for the pattern. And so the Knuth-Morris-Pratt algorithm is an algorithm that determines whether or not the pattern occurs in the text. And it does it in linear time, and with only a little bit amount of memory. And so I want to describe how this works. I'm going to, for sake of time, use a bit of a smaller piece of text, but we'll use the same pattern. And if you look in a textbook for this algorithm, you might see something that looks like this. I took this from a standard textbook on algorithms, not to pick on anyone in particular. They all look something like this. And as functional programmers, we can squint at this, and we might be a little bit grumpy about having to look at a for loop and a while loop, but we can make sense of this. And you can see that there's this compute prefix function, and it turns out that this is actually doing a lot of the work here. It's populating this pi variable, which is an array. So if I take a look at this procedure, and I stare at it for a little while, you see we have these nested loops. You see that at the bottom, we're populating this pi array. And if you look for longer and longer, you say, well, there's something kind of weird happening where actually while we're populating this array, we're actually also reading from earlier bits of the array. And at least for me, I got my head kind of tied up trying to figure out what was going on here. So I wanted to see if there was a nicer explanation for this algorithm. And I want to show that to you kind of in a pictorial way, so with some images. So the starting point for this algorithm is an NFA that will implement this substring search. And hopefully this is kind of intuitive. This might be what you would write initially if you're thinking about, OK, well, what is a less naive version of substring search? I'll construct the following NFA. So you can see that for every prefix of the pattern we're considering, we have a state in this NFA. And we have just a straight line of transitions for each of the characters in the pattern. And so if we had just had this straight line, that would be a DFA, and it would just match the pattern at the beginning of the text. But in order to make this substring search so that the pattern can occur anywhere in the text, we're going to include this self loop at the beginning, with just this star, which I'm going to use to indicate any character. Okay? So that's what makes this particular thing an NFA. And we would run this on the input text, so we can simulate the NFA. And of course, to simulate an NFA, we're going to keep track of the set of states that we're currently located in. So I'm going to indicate that just by highlighting the states in this NFA. So at the bottom, we have a set of states. It's just a singleton at the moment. So we're going to start running this NFA on this input text. And I want to mention, maybe just for reference, what you should be thinking about when you look at this set of states at the bottom. You want to think of this set of states as representing candidate matches. Okay, so as we're going along in the text, we are going to start looking for possible positions at which the pattern can occur. And all of the candidates are going to be inside of this set at the bottom. Okay? Right, so at the very beginning, we're going to start an empty candidate, and because we haven't looked at any characters yet. Okay? All right, so I'm going to just simulate the NFA on this piece of text. If we see an A, nothing happens. If we see an M, we're going to end up in two states, one in which we've seen an M, because that's the start of our pattern, and another which is always empty, because we can always start looking for the pattern at any position in time. And now we're in the point in the text where we're actually going to see this pattern. So we're going to see M, A, M, A. Okay? And so we end up in these sets of states in our NFA. And we're at the accepting state, so we know we saw the pattern at a specific point in time. And we can keep going. If we were looking for to count, for example, how many instances the pattern occurs or something like that. We would keep going and just count how many times we reach the accepting state. OK, so that's one way of approaching this problem. I want to give the two main ideas of what makes this Knuth-Morris-Pratt algorithm work. And it's close to the NFA, but it exploits two pieces of structure in that particular NFA. And the first idea is that there's only n+1 sets of states possible. So if you took that NFA and you determinized it with the power set construction, in general, right, because it's the power set construction, you get sets of states, you may get exponentially many states in the worst case. But for this particular structure, we have this line of states in the NFA and a single self-loop at the beginning. You're actually only going to get n+1, where n is the size of the pattern that we're looking for. And that's very nice. And so it turns out that we don't get this blow-up if you determinize. You get something like this. Now, maybe to explain a little bit about why that is. So suppose you were at this position in time. You have just read the pattern inside of the text. And we're thinking about what kinds of sets of states that we could get at the bottom. So if we've actually read the pattern, we've read mama, we can think about what the other candidates are going to be in this set of states. And it turns out, because once we've known the longest one, we've actually determined what all of the other ones are going to be, because they're actually contained within the longest candidate. So we can see that we have this red one, which is contained as a suffix of this longest candidate, and also, of course, the empty one, which is always present. So once we fix that longest candidate, then everything else is determined. So what that means is that there's only the number of prefixes in the pattern. That's the only number of DFA states that we could have, which is n+1. OK, so that's the first insight. So that tells you if you did the power set construction, you would only get a small amount of states. But there's another insight here that leads us to this algorithm. Oh, and here's what that DFA would start to look like. Now, if you did the power set construction, you would fill in all of the other edges in this DFA. But actually, that's not the Knuth-Morris-Pratt algorithm, just doing the minimal DFA construction. It's actually a little bit smarter than that, and we're not actually going to generate all of the other edges in this automaton. We're not going to generate the whole transition function. We're going to do something else. And that's where the second idea comes in. And the second idea is that each of these state sets contains within it an earlier one. Okay? So I'll show you what I mean by that. So if we look at this first, or the second state, you can see it's comprised of 2 bits. We have the top part, which is m. That's the longest candidate we've considered, as well as the bottom part, the tail of this set, which is exactly the first state. You can see that here. And that holds true of this third state. We have MA, the longest so far, as well as the tail part, which is just epsilon. That's the first one. That holds true of the fourth. So we have MAM. And then the rest of this, the rest of that set, is the second state. You'll see that. And then finally, that holds true of the last one. So we have mama, the top. That's the longest. And then we can see the tail is actually, in this case, the third state, an earlier state of this DFA. OK? Now, once again, we can think a little bit about why that actually holds. And so once again, I'm going to consider the same scenario we were in before. We've just read the entire pattern in this text. And we've seen this set at the bottom. And we can imagine what would happen if we got a slightly different text. So imagine we have just changed that first character of the match of the pattern in the text from M to something else. It doesn't actually matter what it is, as long as it's not M. What that will do is that will remove the longest candidate from this set of states. So concretely, imagine this was B. Then we would end up with this smaller set of candidates. And because we've only changed the first character of the match, of the pattern, then we're only going to remove that longest candidate. And so it turns out that the tail part of the subset is actually a legitimate state of the DFA because we could have run it on this initial text to begin with. OK. So that relationship with the subsets that I described earlier, you can draw that actually on the automaton in these dashed edges. OK? Right, so combining those two insights will give us the Morris-Pratt automaton. And it looks something like this, which combines those solid edges with those back edges. So just to briefly describe how this works, when we're going to run this automaton on this input text, the successful matches will go along the solid edges, and that will consume input. But when we get a failure, what's going to happen is we're going to go back along these dashed edges, and we won't consume input. We'll try again, of course, until we get to the beginning, and then we have to stop. So let me just go through that process on our example text. So we see an A, we don't move. We stay in the same place. We see an M, we go forward one. That was a successful transition. We see an M, that's going to be a failed transition. So we're going to go backwards along the dashed edge. But like I said, when you go backwards, you don't consume input. You're going to try again. So we're still at M, so we have a successful transition now, and we go forward. OK, so we're going to see now a bunch of successful transitions, A, M, A at the end. And now if we wanted to keep going, we see another A, and we're going to go backwards. This is a failure to the middle state. And once again, backwards to the very end, or to the very beginning, I suppose. OK. So that's the Morris-Pratt automaton, which is almost the whole thing. OK, those two ideas, those two key ideas, and combining them into that kind of automaton is the key idea of the algorithm. There's just one more twist that will deliver the full Knuth-Morris-Pratt automaton, which is the idea behind the Knuth-Morris-Pratt algorithm. And that idea is to make one more observation about how you can kind of short-circuit some of these backwards transitions. So I want you to consider this fourth state. And what happens if you have a failure at that fourth state? Okay? So if you're at the fourth state, you have a failure, which means, say, for example, you saw B. That means you're going to go backwards to this state here. And we're going to try again with the same B. Oh, well, we're going to go backwards, of course, because that doesn't match. Now, you can see that the successful character on both of state 4 and state 2 are both A. So if you went backwards along this dashed arrow, you would always, because they're the same successful transitions, you would always follow this one again, all the way back to the beginning. Which just means that we can compress this a little bit by just going directly there. Okay? So we're going to just observe in the Morris-Pratt automaton some of these transitions that we can shortcut, that we can glue together and merge and go and take a longer jump backwards. Okay? And that's the essence of the algorithm. Now, just to connect it back to what we saw earlier, so remember I mentioned this compute prefix function and this pi array thing. It turns out that this pi array is essentially just encoding those backward dashed edges. That's what that is representing. So that's the key bit of information that you need to compute. And it represents the backward edges in the Knuth-Morris-Pratt automaton. That's what's stored in that pi array. OK, so that's what I have. There is some more in the paper. So what I presented to you here today was a little bit quick, of course, because it's a talk. But in the paper, there's actually a very, very gradual progression that doesn't start from the NFA. It starts from just naive substring search and has pictures for each of these steps. And you gradually will develop the KMP algorithm very, very, very gradually. And the explanation that I provide in the paper is also intended to be very self-contained. So it's intended to be able to be communicated to, say, freshmen, undergraduates, who have just taken their first functional programming class and don't have any knowledge of automaton. So I kind of hide some of the automata there in the paper itself. Of course, we don't have time to do that, but it's a very gentle introduction. And of course, I didn't show any code, but in the paper, there is a Haskell and Racket implementation. And Haskell is especially nice for implementing this algorithm because that cyclic structure of the automaton can be very, very easily realized with laziness. Okay, so you can actually see the implementation at that link. Okay, thanks very much.
We have time for a question or two.
Hi, Kimi Yo, no affiliation.
Hello.
I'm afraid you've lost me very early in your talk. Have you considered giving type signatures to some of the maps for us to help us understand your contribution better? For instance, in the imperative code from the algorithms textbook that you gave, I think there was this reference to this one function. And I think that you are reusing that, so perhaps just giving a type signature will help. Presumably it's in your paper, yes?
So in the paper, one of the things that I do is that you have each of these sections that incrementally develop the algorithm, and each have a different data representation. So all of the functions have their type annotations attached to it, so you can see how you're using different data structures as you go along.
Okay.
Yep.
Hello. Now, excuse me if this is a very naive question. I do like your presentation, but did raise the question for me of how does this compare with the minimal automaton, and why is this better?
Yeah, so the minimal automaton will have a lot more of these. So here you can see these backward transitions. There's only one per state here. If you construct the minimal automaton, you're going to potentially construct lots and lots of back edges for every other character in the alphabet, presumably, potentially. So really, it's about saving memory. So this is a much smaller amount of memory to store this than the minimal automaton.
Okay, then does this alternative style of automaton generalize to other types of problems that we would frequently use a normal automaton for that's like, it would be better?
That's a good question. I don't exactly know the answer to that, but I do know this kind of automaton is a construction that people have considered before. In particular, it's called a two-way DFA.
Two-way?
Two-way, yeah. And that's in the paper. You can look at the reference for that. Two-way.
W-A-Y or
two-way.
Okay.
Yeah.
Jakub Bachurski, University of Cambridge.
Sorry, I think we're out of time.
Okay, cool.
I apologize.
That's right.
Thanks very much.
Thank you.